So in this short video, I'll talk about voltage, why sometimes there's voltage rise, also known as Ferranti effect. When we think about a system, so if I draw a system, for instance, I have, sending end, so V sending, so the sending end voltage, so you have some system here. Let's say this is a line, for instance. So it's going to have resistance, some reactance. Obviously, it's going to have some charging capacitance, sometimes referred to as B. Then you're going to have the receiving end, so V receiving, or the voltage of the receiving end. I'm going to make up a number here. Let's say the voltage here is 1 per unit, or 100% of the rated voltage. That we assume, or what's intuitive or common sense, that the receiving end will be reduced because you have voltage drop across R and X. In other words, you might see something like 0.95%, per unit, or in other words, this is 100% of the rated voltage. In other words, if this is 345 kV rated line, the voltage here is 345 kV. But here, the voltage will only be 95% of rated. In other words, 95% times 345 kV. And if I do the math, so it's the voltage would be around 327.75 kV. So it's less. This is what we normally understand. It makes sense to us. So typically voltage is higher at the sending end, but as you go downstream, you're gonna incur voltage drops, across any resistance or reactance, of the lines, transformers, and so on and so forth. The voltage rise issue can take place under lightly loaded or open circuit receiving end conditions. However, there are cases where actually the opposite happens. In other words, if this is 345 kV, you have a line again, you have a receiving system. The voltage could be, let's say if this is 100% of rated, this could be 110%, for instance, which would be 1.1 times 345. So it could be 379.5 kV, which intuitively it does not make sense, because we know as you go down, voltage drops. The reason being is because when you have a system that's lightly loaded, in other words, there's less load to consume voltage and kind of bring that voltage down, then you're going to have voltage rise. Or if somehow this breaker here is open, then we might ask why, if this breaker is open, load current is 0, why do we have that voltage rise? The problem is you have that shunt reactance or susceptance, because you're going to have a lot of them, and then so you're going to have some capacitive current basically flowing through the line, even if the load current is 0, which leads to voltage rise basically. So this is known as Ferranti effect. So the voltage rise under these conditions gets worse with very long transmission lines and voltages. Typically as voltage is higher than 300 kV, it really gets worse, and especially if they're very long, So the capacitive shunt susceptance contributes to the voltage rise at the receiving end, because when you model when you have a transmission line, for instance, so you have reactance and you have inductive reactance, resistance and inductive, but There is also the susceptance, you know. If it's for like short lines, typically it's ignored. But if you have a medium line, typically what you do, you take, so this is sometimes referred to as Y, sometimes B. It's the shunt reactance or susceptance, basically. Basically what you do, you take half of that and you put it on each side of the series impedance, basically. If you have a very long line, typically, I realize I made a mess here. So what you do, so typically you put the entire susceptance here, kind of in the middle of, I'm just going to call this impedance, 1/2 of that line impedance. You put the other 1/2 here. But really what kind of contributes to the voltage rise is these susceptances here. And again, this gets worse because as the because they provide VARs, basically capacitive VARs, which kind of leads to the voltage rise. So one mitigation to this issue is to install a shunt reactor. So basically at the end, again, you have a receiving end, you have, so V sending, V receiving. So basically at the substation here, you would install a shunt reactance. So shunt means it's connected line to ground, basically. So it has some XL 2 pi FL inductance, basically, because we know inductance absorbs reactive power, basically. So what it's going to do is it's going to bring the voltage down. So it depends. You can install static. In other words, either the reactance is either in or out. So the entire reactance. So you cannot do like increments, for instance, or stages. Or you can have variable reactors. In other words, you can change the reactance as the voltage changes. Because sometimes, you don't want the entire reactance or the entire reactor to be in reactance. You want like just some of it, because it depends on the voltage rise, But you can have a variable reactor for this application. Variable reactors, basically they have load tap changers, LTC, load tap changer, which vary the voltage basically and VARs by, basically you only include so many turns in the circuit, it depends on voltage, so it will be programmed, and if you have like 10% up and 10% below nominal voltage, so you can change the taps from in, so like as one application, for instance, you have like typical LTCs, you have plus or minus 10%. In other words, if this is the nominal, then you can go up from nominal up to 10% of the rated voltage, or you can go below the nominal, 10% in increments of 5/8 or 5/8% or 0.625%. These are the steps. So you can go like 1 times. So you're going to have 16, typically, again, I say typically because it depends on design. You're going to have 32 taps total with, when you are in the above, so when you are in the raise, condition, you're going to have 16 taps. When you are in the lower, you are going to have 16 taps. So you're going to go from tap 1 all the way to tap 16, and each tap you're going to change the voltage by 0.625%. So tap 1 times 0.625%. Tap 2 is 2 times 0.625. Tab 3, it's 3 times 0.625%, up to 16 if it's raised, 16 times 0.625%. So you can change that way. It's better because the voltage change is kind of more controlled. It's smoother, and rather than the entire reactance is you do it in increments. So, but the problem is this adds to the complexity, which also leads to obviously cost increase and also weight increase, because you're going to have a low tap changer, you're going to have extra turns. So you have to account for all that and make sure it's designed properly. Shunt reactors have gaps. So basically the core of the shunt reactor has gaps to control the reactants basically. These are typically oil filled, because you can have shunt reactors that are dry or air they have air as their core, But the ones, that are used to control voltage or bring voltage down under light load conditions, or like when one side is open, these are typically oil filled. So power flow simulations, can be performed to produce the appropriate shunt reactor size, like megavars basically. So you can say, okay, how many megavars I need in order to bring the voltage down, or absorbed by the reactor. And so power flow solutions will kind of do that. So some control logic will be implemented to avoid having the shunt reactor in service during peak load conditions, which would exacerbate voltage drop. Because under peak load conditions, so you have the sending end voltage, receiving end voltage. So under peak load, VR will be smaller than VS. In other words, the receiving end voltage will be lower than the sending end. Let's say this is 0.95 per unit, or 95% of the nominal voltage. Well, now if you have that shunt reactor in service, it's going to drop the voltage even further. It could drop it to 0.9 per unit, or even more than that. We don't want that, because that's not good, especially where some loads depend on voltage, voltage quality. So that's why you need some kind of logic, where, and like today, for instance, most substations are peaking in the summer, for instance, but that could change, So in the summer, probably you don't want the shunt reactor in service. Probably in winter or when in seasons where the load is lower, But the bottom line is you want to make sure you don't forget that shunt reactor, in service, which could lead to very low voltages, under peak load conditions. So switching of shunt reactors, is critical and needs to be studied carefully from operation perspective, because you have to have the proper breaker to do that, and that's something you have to convey in the specification of the breaker, like what is the application of the breaker, because it's not just a normal breaker. I mean, the construction is the same, but manufacturers, they have to take into account other factors, So you have to be very clear that this breaker is for switching in and out a shunt reactor, and you provide the size and so on and so forth. That way, it's designed properly, like how to interrupt current, because now you have an inductance, So they have to take all that into account. Thank you and have a great day.